Hello YouTube, it's Troy here and welcome back to the channel of The Lonely Wolf. So today we're going to dive into our next video on the philosophy of mathematics. So this is going to be part 3.1. So the next topic is we're going to be looking at logic. Okay, so for those of you who followed my little mathematical journey along the way, and I do thank those people who watch, so our first video we looked at the metaphysics of numbers, so we looked at the inherent existence of different types of numbers. Then in the second video we explored the mathematics of aesthetics and beauty, which is another branch of philosophy. So in the next few videos, which I'll break up into several parts, we're going to focus a bit about logic. So in today's lesson, we're just going to look at the deductive and inductive reasoning. So we're going to go through a few examples together and explore the difference between those, and we'll look at the process of mathematical induction. So as I said before, it's going to be called part 3.1. So the logic series is going to go for a few videos because I think there's a lot of different topics we can dive into. So some of these we're going to get a little bit more mathematical, so don't worry if there's some sections that you don't really get. So hopefully you get the overall idea of deductive and inductive. So let's dive into this. So we're going to start by defining what deductive reasoning means and what kind of thought processes are involved. Alright, so these diagrams are really good at explaining the concept. Alright, so let's start with the orange part. So what we're doing is we're starting with the truth. Now from that we have to apply additional truths, and when we're applying additional truths we're justifying our reasoning along the way, and from that we arrive at a new truth. Okay, so in essence what we're doing is starting with something that is true. So for example, it could be a scientific law. And from that, we do a little bit of gymnastics and we arrive at a new truth. Now, it's also known as a top-down. So we're starting off with a very large idea and we're narrowing down to something that's a bit smaller. Now, the example on the right is a really very easy to follow example. So let's start off with a truth. So all oranges are fruits. So that's a truth we're starting at, and we're building a new truth. So the next statement is all fruits grow on trees. And so therefore it follows that all oranges grow on trees. So see what we've done there. So we've started off with something that's universally true, that oranges are fruits. Okay, and then we apply another truth. So the additional truth is that all fruits grow on trees. And therefore we've arrived at a new truth, which is all oranges grow on trees. Okay, so we've started off with a larger truth and we've narrowed our way down. So we've done a top-down type analysis. Let's contrast that with inductive reasoning. So it's actually the opposite. So we're starting off at a small scale and we're going from the bottom up. So what we're doing is we're starting with an observation. And so from those observations, we infer certain patterns. So we develop a hypothesis and we might work on trying to prove that hypothesis, or not prove, but to support the hypothesis, and we come up with the theory. So the theory is not something that's set in stone as a universal truth. Okay, it's something that's strongly supported. And so it might be true or it might be false. So I guess the strength of our theory that comes up, so we can convince people of the validity of our truth if we've made good observations and if we've been very good at applying the patterns. So there's a lot of things that can go wrong during the process. Now this is worth noting that inductive reasoning is something just about all of us are using. So no matter what type of argument you're getting into, so you could be on a YouTube debate, you could be trying to debunk a YouTube video, or you could be making a video of your own to come up with a theory. So we have to remember we're not dealing in absolute truths. So we shouldn't be trusting people who say, I've proven this YouTube video is wrong. I've proven that this tweet is wrong. So we haven't exactly proved anything because of the fact that we are operating from a place of induction. So what we're doing is we're starting off with an observation. Now that theory is likely to be weak if our observations have come from a source that might not be reliable, or if our skills at looking for the patterns from the observations has been questionable. That can also lead to a very weak type of theory. So a lot of things can go wrong in inductive reasoning. Now when it comes to a deductive reasoning, we are starting with true facts and we're arriving at a sure conclusion. So usually that involves a scientific law. But when it comes to induction, we're interpreting evidence that's being presented to us and we're coming to a possible conclusion. So at the end of the day, we become better YouTubers, so our videos are probably better and people will take our arguments more seriously if our evidence is good. So if the evidence has come from a lot of sources and we've gathered a lot of evidence, then our conclusions might be a little bit more closer to being correct, more likely to be correct, because we're surrounded by probability. Now, if we've presented weak evidence or anecdotal evidence, and we haven't really cited our sources, or our sources are questionable, then our conclusion is probably going to be just as questionable. So remember, we're really looking at probabilities when we do this. Now let's drill down specifically into a discipline. So this is an example of a thought process that I had to go through. So this was an assignment that I did when I was studying history in school. So our task was to develop a hypothesis, basically, or a working theory. So we had to make a theory about two civilizations. So I did that. I chose two civilizations. I chose Crete and I chose the Persian Empire. Now, the first step was I was trying to collect evidence. So there were pieces of information and I was trying to look for a pattern. So during this process, the evidence that I chose is I chose a lot of artworks, but then there's also other things we could choose. We could choose like written records and a lot of other sources as well. So if I look at the top panel, which represents the Minoan art, so what we're looking at is there seems to be more of an interest in nature. It seems to be free flowing a little bit more, and it seems to be a bit more carefree. And there also seems to be, socially, there seems to be more of an egalitarianism. So we have on the left pane, we have women who are dressed up very well and they seem to be highly regarded. Then on the right-hand panel, there's bullfighting type artwork in which there are both boys and girls depicted in this sport. So it seems to suggest that there might be, more of an egalitarianism. But if we look on the bottom panel, we see a society that's not as carefree. It seems to be very rigidly organized, and it seems to be depicting soldiers and marching and warfare. And it also seems to be a bit more patriarchal in that there's no women in those figures. Now, this doesn't really prove anything, okay, but it does help me to look for patterns, and from those patterns, I infer a theory. So that theory, so the strength of the validity of that theory will depend on how well I present the evidence. So that means I'll have to collect a lot more artwork, and I'm going to have to look for more supporting evidence of other sources such as historical records or written records or historical facts. And so the more that I have, then the more likely that my theory will be taken seriously and I'll get a better mark by the teacher. Let's drill down into the process of mathematical induction. So this is where people may encounter difficulties, but that's okay. All right, so this is what we do. So usually in mathematics, we're going to encounter numbers, and from those numbers, we're going to see patterns. So once we observe certain patterns from numbers, we can create a theory, and then we want to test that theory. So that is the process of proof by mathematical induction. And if we prove that theory, we can show that it's true for all cases. Now, the patterns usually occur in steps. So step 1, 2, 3, and 4. So for example, the first number, the second number, the third number, or the observations are numbered in a very logical order. And n is thought of as an arbitrary number. It can stand for anything that we want it to be, as long as it fits a certain set of parameters. Okay, so this is the basis of the proof. So at the end of the day, what we want to prove is the following statement. Okay, so if the first n propositions are true, so remember n is some kind of arbitrary number. So if we're assuming that that our theory is true for the first n numbers, it follows that the n plus 1th has to be true. Now, we're not stating this, we have to prove this. So we have to prove that the left-hand side implies the right-hand side. So if we assume the left-hand side is true, then we have to prove that the n plus 1 is true. And that's where the real work is. Okay, that's where most of the difficulty is in doing that, because we have to do a bit of algebra for that. So these are some of the steps. All right, so step 1 is we have to prove that it's true for n is equal to 1. So if we observe a pattern, we have to look at the first case. Now, if we can show that P1 is true, this is the basis of our proof. So to illustrate this, we're going to do an example. So there's going to be a little bit of algebra. So if you can follow, that's great. But if you don't really follow what I'm doing, you're not going to miss the overall large picture of that. Now, if it's true for the first n, it follows that n plus 1 is true. And so we have to prove that the logical statement is in fact true. So we have to prove that this is. Okay, so that's the step. So looking at 1, and then looking at n, and then looking at n plus 1. Now the best way to do this is by way of an example. So what we're going to be looking at is a sum of the odd numbers. So for example, 1, 3, 5. So we're going to add up. So the first one is we're going to put 1, and then the second one is going to be 1 plus 3, etc. Now we notice a particular pattern. Okay, so the first number is 1, the second number is 3. So it's usually multiplied by 2 and taking away 1. So for example, if it's 1 okay, we multiply by 2 and we get 2, and take away 1, we get 1. And then if we go the second term, so 2 times 1 is, 2 times 2 is 4, and take away 1, we get 3. And so the next one must be 2 times 3 is 6, take away 1 is equal to 5. So that's the basis of odd numbers. Anyway, let's continue and let's watch this video all the way through. So this is me doing it, by the way. So it just goes 1, 3, 5, etc. Now, as I said before, what we're looking at is we're looking at the sum of these odd numbers. Now, our first sum is just going to be 1. But before we do that, we might just number our terms just for ease of explanation. So 1, 2, 3, 4, 5. So we'll label them according to their place. So the first sum is just going to be 1. And the second one is going to be 3 plus 1. And that's going to give us 4. So 5 plus 3 plus 1. So adding up all the previous terms, we're going to get 9. And then 7 plus 5 plus 3 plus 1. We add those up and we will get 16. And we'll just do one more, just for the sake of it. 9 plus 7 plus 5 plus 3 plus 1 gives 25. So we can actually observe a pattern here. So the pattern we're observing is these numbers are square numbers, or numbers that are multiplied by themselves. So for example, 1, and then 2 times 2 is 4, 3 times 3 is 9, 4 times 4 is 16. So what we're going to do from that is, from our observations, we've seen a pattern, and we're going to develop a theory. So that means that all the way up to, the next one is 2n minus 1, that's the nth odd number. So we're going to say that it's equal to the square if we add up all of the odd numbers. That's our theory, and now we have to prove it. Now before we do that, we have to start with step 1. This is the basis of our proof. So we've got to show that it's true for the first number. So that the left-hand side and the right-hand side have to be equal to each other. So the left-hand side is just 1 because it's only one number, and the right-hand side is going to be 1 squared. And 1 squared is equal to 1, and because they're equal, we've shown the basis of the truth that it's true for n is equal to 1. Now what we have to do is go through the induction process. So this is the if. So if it's true for the first n terms, we have to prove that it's going to be true for the n plus 1. So the one above that, we have to show that it's true. We have to prove this is there. Okay, so to translate the left-hand side, so P1 up to Pn, we just have to repeat that theory. So we're going to assume that this is true. So from that, what we have to do is look at the next term. All right, so we're looking at all the way up to the nth, and then we have to look at n replacing with n plus 1. So put n plus 1 in a bracket, and then take away 1. So just replacing n with n plus 1. Now the first part of the series is going all the way up to n, so we know that it's going to be n squared because we're assuming it is, and then we plus just our last term that we've added on to that. We're going to expand some brackets out there, so if you're good at algebra, you'll enjoy this. So 2n plus 2, take away 1. And we simplify that, and 2 take away 1 is going to give 1. Now, if you're good at algebra, you'll know that that expands, it simplifies to n plus 1 squared if you do that. And if you expand it, you'll get n squared plus 2n plus 1. So what we've shown is that the sum of the first n plus 1 numbers is n plus 1 squared. Now that's what we've sought out to prove when we were doing our proof. So therefore we've proved that it's true. So this particular pattern and this theory is true for all values of n. But we've kind of restricted ourselves on the value of n. So what is the value of n? So this is called a domain when we're restricting what n is. So n is defined as obviously positive numbers, and they have to be whole numbers as well. So 1, 2, 3, 4, 5. Okay, so we can't have decimal places. Okay, so that's what it really relies on. So we have to be careful to define what n is. So it's true for all values of n, as long as n are positive integers. Let's have a look at exercise. So this is a thought exercise. It's going to get you thinking, and it really stumped me a little bit. Okay, it's called the cow conundrum. Now, let's assume that there's a cow, so as a baby, known as a calf. So let's assume we're allowed to pick it up. Okay, so the assumption is that, let's say that today I can pick up the calf. So what we can assume is that overnight, the cow hasn't really grown, has it? Okay, so it hasn't grown significantly that it's going to weigh more. So on the next day, we can pick it up again. Okay, so that's the basis of that. Now let's say that we chose some arbitrary time period. So let's say it's n. Okay, so time n. So up until that particular point, we can assume that we've been able to pick up the cow. What about the next day? So that's going to be n plus 1. Well, if we could pick it up the night before, then it makes sense that we can pick it up the next day. So we've actually gone through the process of mathematical induction, and you know, in a strange way, we've made this proof that, you know, we can pick up a cow whenever, but eventually there reaches a time where that cow is no longer able to be picked up. So it doesn't make logical sense in the real world. Okay, now let's have a look at why this didn't work. Okay, so that's the thing that really stumped me. So let's have a look at some of the precepts. So some things have not really been defined well. So for example, the reason why the first example, which was the sum of the odd numbers, the reason why that was easy is because the numbers are well defined. Okay, so we know that they're whole numbers, 1, 2, 1, 3, 5, etc. So we know that their sequences are 1, 2, 3, 4, and the value can go up to infinity. Okay, so we can go up to any number we want, but the numbers are not as well defined when we're looking at the lifetime of a cow. So let's say that we defined n as the number of days. Okay, so immediately we find something wrong with that because we can't really define that very well. So the cow eventually has to die, like all animals. So therefore we can't really define n, so we can't think of it as an infinity. So therefore our place where we choose that day n to look at n plus 1, we can pick up the cow. It hasn't been really well defined because, you know, it's not going to be infinity. So for each cow, it's going to be a different set of restrictions we're going to have on the time period we're looking at. The other thing we haven't really defined very clearly is, you know, what it means to actually pick up. So the definition of picking up the cow. So does it mean we can pick it up very, very easily? But then the next day, you know, gradually there might become a time where it becomes more difficult to actually pick it up. Okay, so you might be barely even holding it just above the ground. Whereas if it's a calf, you can lift it up very easily. So the definition of lifting hasn't really been specified in a very great detail. So because of some of those reasons, that's why that works out. And maybe if you think deeply, you'll find other reasons or other flaws behind this conundrum. Okay, so even though logically, yes, it might be, we might assume that yes, on this day I can lift it, and if we know that the weight hasn't gone up significantly overnight, then we should be able to lift it the next day. So it's an example of seeing a process of mathematical induction, but then when it translates to, you know, real world situation, there are some complexities there. Okay, anyway, that's me. So this is my video on inductive versus deductive reasoning. Alright, so join me again in my next video. So I think we will have a look at, so what I was thinking we could look at is set notation. So some of the logic notation and some of the mathematical tools we have to express different logical statements. Okay, so join me next time, and if you're new to this series, so please check out my other ones. So if you've enjoyed this video, please press the like button, share me around on Twitter, subscribe to my channel, and share my things around if you like what you see. And I'm sure you did enjoy it. Okay, thank you very much, and I'll see you again in my next video.